In many applications, a very pure form of a specific metal is required. One method used to purify metal is called electrorefining. It uses a type 3 electrolytic cell. The most important thing to know for electrorefining is the anode is an impure sample of the metal we want to refine. Remember, the anode is connected to the positive terminal of the power supply. And the cathode must be a pure sample of the metal we want to refine. Remember, the cathode is attached to the negative terminal. In this video, we'll use the electrorefining of copper as an example. On the impure anode will represent an assortment of atoms, mainly copper, but with some impurities. And on the pure cathode will represent all copper atoms, as this is pure copper. We'll add some aqueous copper 2 sulfate to the cell. If we're going to purify copper, we must have copper 2 plus cations in the electrolyte. Neither water nor sulfate ions will react in this cell, so we'll remove them from our diagram. We'll focus on the anode and we'll add a section of the right side of our reduction table. We'll zoom in on gold, copper, and zinc. We'll just point out here that we use the solid copper at 0.34 because this half reaction represents the reduction of the more stable copper ion, Cu2+. We don't use the one at 0.52 because this represents the reduction of the copper plus ion, which is unstable in aqueous solution. Copper is the metal we're purifying, so the impure sample is mainly copper atoms. The gold atoms we added can represent any metals that are above copper on the right side of the reduction table. This includes gold, silver, and mercury. Anything we say about gold on this video applies equally to all metals above copper on the right side of the table. The zinc atoms we added can represent any metals that are below copper on the right side of the reduction table. These include metals like lead, tin, nickel, cobalt, iron, and chromium. Even metals below zinc that are not shown on this diagram, such as aluminum or manganese. Anything we say about zinc in this video applies equally to all metals below copper on the right side of the table. Now, if we consider gold, copper, and zinc, we see that gold has an oxidation potential of negative 1.5 volts. Copper has an oxidation potential of negative 0.34 volts, and zinc has an oxidation potential of positive 0.76 volts. The question now is, which one of these metals will be oxidized first? The answer is zinc will be oxidized first. It has the highest oxidation potential of all three, and is lowest on the right. Looking at this zinc atom, it will lose 2 electrons to become a zinc 2+ ion, which will then leave the electrode and go into the electrolyte. The half reaction for the oxidation of zinc is Zn gives Zn2+ plus 2 electrons. Additional zinc atoms will be oxidized to the zinc 2+ ion, which will leave the electrode. This will happen until all the zinc atoms are gone, and zinc no longer remains as an impurity in the impure copper anode. The metal with the next highest oxidation potential is copper, with an oxidation potential of negative 0.34 volts. So a copper atom will be oxidized to a copper 2+ ion, which will leave the electrode and go into the solution. The half reaction for the oxidation of copper atoms at the anode is Cu gives Cu2+ plus 2 electrons. Copper atoms continue to be oxidized into copper 2+ ions and go into the electrolyte solution. Because gold has such a low oxidation potential, it cannot be oxidized as long as copper atoms are still present in the anode. As all of the copper atoms surrounding gold atoms are oxidized and leave the electrode, there is nothing left to hold the gold atoms up, so they will simply fall down onto the bottom of the container. It is important to remember that this gold has not been oxidized. it is still a neutral atom of gold metal. Metals above copper on the right side of the table will fall off of the anode in metallic form and collect below it in the container. A combination of metals that are above copper on the right side of the table, which do not get oxidized, such as silver and gold, along with the non-metallic impurities that were in the copper, will collect underneath the anode. This is often called the anode sludge. Later on, this is refined to extract the precious metals from it. Copper atoms continue to be oxidized to copper 2+ ions that go into the solution. Now we'll focus on the species above copper on the right side of the table. We had left sulfate and water out of our diagram, but remember they are still present. Sulfate has a very low oxidation potential of negative 2.01 volts, and water, with its overpotential effect, behaves like its oxidation potential is about negative 1.38 volts. So we might think that after copper is finished oxidizing, that water will be the next species to oxidize. However, the whole process is stopped before all the copper has been oxidized. So neither water, nor gold, nor sulfate will ever get to be oxidized. So once this process is stopped, the only cations in the solution are cations of metals below copper on the table, like zinc 2+, and copper 2+ cations. There are no cations of gold or any other metals above copper on the table. These will not be oxidized, so they will not form any cations. They remain as neutral atoms. Now we'll reveal the cathode again. Remember, reduction of cations occurs at the cathode. The reduction potential of Cu2+ ions is positive 0.34 volts. It is considerably higher than that of zinc 2+ at negative 0.76 volts. So Cu2+ ions will be reduced at the cathode. But Zn2+ ions will not be reduced as long as Cu2+ ions are present, because Cu2+ has a higher reduction potential than zinc 2+. So we'll remove the zinc ions from our diagram. Remember, while the cell is operating, copper atoms are being oxidized at the anode, and copper 2+ ions are continuously added to the solution. So copper 2+ ions in the solution are never depleted. Focusing on the cathode, as the cell operates, copper 2+ ions will be attracted to the negative cathode and will be reduced to neutral copper atoms. The equation for the reduction of Cu2+ is Cu2+ plus 2 electrons gives Cu solid. This process will continue, and copper 2+ ions continue to be reduced to neutral copper atoms as more ions come in from the anode where they are formed. We see that only copper metal is produced and builds up on the pure copper cathode, increasing its mass. So the impure copper anode loses mass as the small amount of zinc it has gets oxidized, the large amount of copper it has oxidizes, and inactive metals drop off without being oxidized. Looking at the cathode, only Cu2+ cations from the solution are reduced and stick to its surface, so the pure cathode stays pure, increasing in mass and size. In this way, impure copper is purified using a type 3 electrolytic cell.